right. I think we'll start, actually, because even though a few people are coming in, I think we can start. So hi, everybody. I'm David. I'm an architect at Proofpoint, which is a security company. We build a bunch of security products for email and cloud. This talk came about basically when I joined Proofpoint about a year and a half ago. It was a little while after we bought a startup which developed a product which turned into the core technology of our cloud security product. And like most startup products, it was built mainly for features and getting customers and stuff like that. And UX came second, and things like scalability and stability a very distant third, right? Which is fine for a startup product. I'm not complaining about that. But then after Proofpoint acquired it, that was pretty much my main purpose in life, to take this and make it scalable and make it stable and not have to wake up every night because something was broken in production, which happened quite a bit at the start. Oh, by the way, disclaimer for any Proofpoint customers who might watch this: this is all in the past. Anything bad I say about the product is not true anymore. It's perfect now, okay? Good. Just in case anyone was wondering. Anyway, so it was really bad at the start, right? Because it was and the main problem with the product was, not only was it not stable, we wouldn't know when it was unstable, right? The worst is when your boss's boss calls your boss in the middle of a sales presentation to ask if the product is working, and that's how you discover there's a production issue, right? If that happens, that pretty much means that your product lacks observability. So, and that brings us to observability, which is the topic of the talk, which is basically the property of a system that tells you how much you can know about the internal state of the system at any given moment. And the purpose of having observability usually, and it's not binary, it's not either you have it or you don't have it, right? It's a large scale. And the purpose is usually to answer questions which fall into one of two broad categories, right? Is anything wrong right now? And if the answer is yes, there are a bunch of other questions which basically sum up to exactly what is wrong and where is it and why it's happening, right? And so if you can answer those questions for any part of your system at any given moment, you have excellent observability. Congratulations, you can go. So let me do a quick survey, right? Who here works on something that's related to production, right? Has a product which is in production? Pretty much everybody. Perfect. We're in the right place. Can you tell right now, if you have like 30 seconds on your phone or your laptop, can you tell right now if the stuff you have in production is 100% working? Who can tell that right now? If I give you 10 minutes. If you have like an hour on your laptop to look at dashboards and stuff, who can say within 1 hour if everything is working correctly? This is very disturbing. It's like half the people. The other half who have stuff in production aren't confident. And this is true. And that generally means either that you just don't want to do it, and that's fine, or you don't have exactly the right tools to give you those answers, right? And this is what observability is all about. You build up the observability of your system to be able to actually answer these questions very easily and efficiently, and hopefully then you connect it to some kind of alerts, and then you don't have to look. You'll get notified if something breaks, and you can go and find it and fix it, right? And so for my experience, right, and it's not just the last company I worked for, but for every company I've ever worked in, observability is not something people invest to initially. Now, it's very trendy right now. There's a lot of meetups and stuff that talk about observability. It didn't used to be trendy. Like most things in tech, things come like waves of hype. So like 5 or 6 years ago, everything was microservices, and microservices were super trendy, and we broke all our monoliths into microservices. And then we discovered there's a whole lot of microservices. How do we deploy them in production? And so containers became very trendy and hype, and everything was about containers like 3 years ago. And then we actually started putting containers into production, and we discovered, holy crap, there's so many containers in production. How do we know if it's actually working? And so now we come to this problem of, okay, well, we need to talk about observability because we have all this stuff we need to look at and actually figure out if it's working, right? And so I don't know what the hype is going to be next year, but probably something to do with, I don't know, machine learning and stuff, or AI. Because you don't want to actually go and do the observability yourself. You want a robot to do it. And so generally, when you go to these meetups and talk about observability, you come up to a Venn diagram that looks something like this. That's very trendy, and it's a way that which I don't like very much, because generally you go to read some observability blog or some meetup or something, and there's usually a guy from a vendor selling something, and then they talk about logs and metrics and traces, which are like the three main technologies you use to gain observability into a system. And usually there's a logo of the vendor somewhere in one of these circles, or maybe in the middle, right? If you go to an Elasticsearch meetup, the circle is going to be really close together, and there's a big fat Elasticsearch logo in the middle. And if you go to a different meetup, like, I don't know, Jaeger or Zipkin, the circle is going to be far apart, and the logo is going to be in one of the circles, because that's what they're trying to sell, right? And I think that's the wrong way to think about it, or maybe not the best way to think about it, because these are not products that you buy, right? It's a way of thinking about your system that you're building, and a way of actually achieving certain goals. Like, I want to sleep at night. In order to achieve that, I need to be able to know that my system is stable in production, and in order to achieve that, I need these following questions answered. And these are a bunch of technologies which can help me answer those questions or build this, this way of looking at the system, right? And so it's not products. Like, if you have logs and you have metrics, do you have good observability? I don't know, maybe. Depends what you do with them, right? Also, you can achieve different things with different sets of technologies. So let's do a quick survey again. Of the three things, who here works on a product which has centralized logging? So whether it's Elk or Splunk or everybody, yeah, almost everybody. So that's what I'm expecting. I'm going to ask the same thing about metrics and traces in a sec. I'm going to make a guess. About half the people are going to answer yes to tracing, and like 10% for metrics, and like 10% for tracing. So who here has a system for collecting application performance metrics? So I want to say, yeah, let's raise hands. More than half, actually. That's pretty nice. I'm not talking about CPU, by the way, not like low-level system settings. I'm talking about application metrics, like how many transactions it processed or logical things that the application does, right? So traces, in this case, before we answer that, I don't mean traces like strace or dtrace, which goes and looks at low-level system function calls. In this case, I'm talking about traces in the modern way, which means distributed traces, which is something I'm going to cover quite a bit in the remaining of the talk, where distributed traces allow you to look at a transaction that spans your entire system. So if you have a bunch of microservices, you can look at a request which comes in from a web API, through all the microservices, find every service it's touched, every database it called, measure all the latencies and stuff like that, and pull all of this data together and look at it as a whole, like the whole transaction, right? So who here has a system which does that in production? It's actually more than I expected. It's like 20%-ish, which is pretty good, right? And so having all of these things together allows you to build stuff which lets you actually look at the system and sleep better at night. Now, this list is obviously, I don't like it because it misses a bunch of stuff. Usually, you won't hear mention stuff like CI/CD, which is a huge component of observability, right? You want to know when something got deployed to production, because if you see a weird spikes on a metrics graph, and the spike correlates with someone deploying a service, that's a really strong indicator. And it doesn't talk about automation, right? So running automation scripts over your production environment to detect stuff. For example, in our product, we run an automation service every 5 minutes, which covers the main flows through the entire system and measures stuff and figures out if everything is actually okay. And if it's not, it goes and alerts people, right? And it doesn't talk about other things which are also useful for observability, but for our purposes, these three technologies cover like 80 or 90% of what you might want to do in your system, right? And so, again, I don't want to talk about observability in the sense of, well, use this product or use that product and it's going to be all great. It's not. It's more of, it's a feature, and it's a feature of a product which is customer-centric, right? It's not something you do on the back end where you collect metrics, and engineers really love metrics and graphs. That's not why you do it, not just because we love graphs, right? Having good observability in a system means that you can actually provide the service that the customer is paying for, right? It's a business level feature, just the same as having a nice UX is a business level feature. We're actually doing whatever application logic your system does. It's a feature you sell to the client, and so observability is the same way, right? A lot of the time, if you have to sometimes go and justify why you want to invest in building all this stuff on the back end, which the customer never sees, and you have to say, well, we'll have to take time away from building features to put in, logging and metrics and instrument traces and stuff like that. And the actual ROI for that is, do you want to keep selling the products to the customer and the customer to be happy? Then we need to build this feature into our system, which will let us actually provide a better service to the customer, right? So as I said, you don't have to have all of these three to build a system which has high observability. For example, our product, for historical reasons, doesn't have distributed tracing is a separate technology, right? So for Proofpoint Casby, which is what I'm working on, we achieve most of what we do with a bunch of metric system. We use StatSite and Grafana and stuff, and mostly logs, right? We use ELK, Elasticsearch, and we overloaded all the tracing functionality, all the distributed functionality on top of the logging infrastructure, which has a price, but it's also very easy because it's something we had in place. So I'll talk a bit about how we can actually do that a bit later. And so you can pick and choose, and the different ways of recording data about your system and looking at it, and different insights you can get from it, have different trade-offs. There are some things they're good at, and there's some price you have to pay for that, right? And so we don't just measure stuff for fun, right? We don't go and collect CPU metrics or whatever, transaction latencies, because it's fun to do that, and we like to know this, even though it is, and we do. We do it because we have a purpose in mind. Usually that purpose is business-oriented. Pretty much everything we do at work, hopefully, is somehow related to actually advancing the business or selling the stuff, right? Because that's what pays our salary. And so generally, you have some sort of service level agreement you have with the customer. It might be explicit, where you actually have a page which says, we have this promise of this service level agreement. The website is going to be up 99.9% of the time, and the request latency is going to be X milliseconds. And it might be implicit, where no one ever bothered to define it, but you have certain expectations of the system, of the way it works, right? I expect my database to return queries in 2 seconds, right? I expect the web page to load in less than a minute, hopefully, right? And so you might have implicit service level agreements, whether it's with yourself or with the product owners or with the customer, whatever it is. And once you have that, and by the way, I urge you to make it as explicit as possible, right? Because implicit expectations tend to be very surprising when you discover they're not actually working the way you expected. And so once you define what your expectation is of the way the system behaves, right? What defines it being healthy? It's not just the server responds. Obviously, that's a prerequisite for it being healthy. But you have to define what it is that makes your system okay in order to be able to then find out when it's not okay. So once we have the service level agreement level kind of settled, then we can define service level objectives, right? So my objective is to have the server up, or X service respond 99% of all the time, right? Which is like a few hours of downtime a year. Or my objective is for the 95th% latency of responses to be within X milliseconds. Then once we define the objective, right, and we have a set of these, we can start tracking those and recording them. And that brings us to service level indicators, where you can define something which looks at the objective and says whether we're inside or outside of expectations for that objective. We can now measure service latency. We can measure end-to-end latency in our distributed system and say, does it fall within our objective? And if it's not, then we can have a clear indication of something is broken. This brings us to actually answering the first set of questions about observability. Is something broken right now, right? Broken doesn't have to mean everything is down, right? The more complex systems, the more distributed systems we build, the more weird ways they have of being not okay, being broken. Like, for example, in our system, it's a large data processing platform. We use Kafka extensively. We have like 80 microservices. Most of them send Kafka messages to each other. At any given moment, 1 or 2 of them can be down, and it wouldn't actually have any symptoms outside the system, right? The website would be up, events would be flowing, but a whole service could be down, and unless we actually have something that tells us about it, we wouldn't know it just from looking at symptoms, right? And so the more stuff you have in your system, the more services and databases, the more ways it has to be broken, or being broken, without you knowing about it, right? And so this is why you define indicators, hopefully to cover all the weird cases where your system is not behaving the way it does. Now, the thing about service level indicators is if you have too many of them, you get into this alert fatigue where too many things can go wrong. It's very hard to calibrate. So I'm going to show you a couple of examples of good and bad service level indicators. We'll start with a mixed case. This is our service level dashboard. It's version 1.0. As always, we have plans to replace it. Everybody has plans to replace anything they're unhappy with. When that's going to happen, I don't know. And so this is something we built when we were a much smaller company. We had a couple of hundred customers, not a couple of thousand as we do right now. So there's a column you don't see with the actual names of the customers. And so what this does, this, by the way, hangs on the wall, on the monitor, right outside where our product owners and the VP of engineering sit, right? This is a business level dashboard. It tells our salespeople and customer support if stuff is broken, because they're the ones who actually really, really deeply care about this, because they're the ones who get yelled at by customers if something's not working. And so there's a rotating list of customers on the column you can't see, and for every other column is a specific feature, a specific flow in our system, and whether it conforms to an expectation, right? And so the good things about this, the indicators are very clear. Something is either red or green. There's no in between, right? We'll look at bad examples later, but here there's no ambiguity, right? If something is broken, you can clearly see it. We also have an alert that goes out and if something flips. The bad thing is there's too many indicators. There's a bunch of red ones over there, and I took a screenshot when the system was not having a good day. And like half of those are real alerts, and the other half are just miscalibrated thresholds where we need to go and recalibrate them because they're actually okay. I know because I checked that they're okay, but it's still showing red, which is a terrible thing, right? It lets you go into this state where you're okay with stuff being red. You should never be okay with stuff being red. If it's red, it needs to be addressed. If it doesn't need to be addressed, it shouldn't be red, right? And so that's why I have mixed feelings about our internal dashboards. But the good things are it's very, very unambiguous, it's very clear, and that's what you want with service level indicators. They need to tell you something is broken. It doesn't tell you what's broken, right? It kind of gives you a pointer, right? If a column that says whatever, login events is red, then I know where I need to go and investigate. This is not an investigation tool. This is an alert and like first response tool. That's what you want in service level indicators. There's a good example here. Who here heard of Reddit? Seriously, there's like 5 people who have heard of Reddit. Thank you very much. Let's wake up. I know it's after lunch. Everyone's tired. You can go home very soon. I promise. So Reddit, right? Big site, has a bunch of users. This is their public status page. By the way, we also use status page. It's a very cool tool, very cheap as that happens. And this is a very good example of service level indicators, right? It has very high level stuff. You can't really see it probably, but it has stuff like web application, mobile application, comment feed, a few others, and like a course level number of requests, and a history going back 80 days or 90 days, right? So it's a very good service level indicator. It tells you if something is broken in a big way, right? I'm sure they have a bunch of internal dashboards as well, but if you just want to know if something is okay or not okay, you go here and you can see it. By the way, status page also lets you subscribe to alerts and stuff like that, right? And so this is the kind of stuff you want for your primary triage, right? This is what you want to tell you, is my system okay or not? And if it's not okay, then you go to all the other things we're going to talk about, which tells you, what exactly isn't okay. And the first thing, which most of you actually have, as we discovered earlier, is metrics. Everybody has at least system-level metrics, right? CPU, disk, all that stuff, networks. But that's the boring stuff. Of course, you're gonna have that, right? If you don't, well, you should. But usually, you want more application-level metrics, right? Because there are things you can discover about the application by measuring something very straightforward, which you can't from system-level metrics. Things like what the latency of a database call is, right? They're very good tools to actually record metrics. The benefit of metrics is they're very cheap to maintain, right? Because metrics are usually time compressed and aggregated, you can store a whole lot of them, right? You don't. The way you store metrics, by the way, in case you're wondering, is you don't store every data point. Usually, applications send metrics to a metrics collector agent, which runs on the machine or somewhere else in the networks, and it collects a bunch of data points over a certain time, compresses them within a certain time unit, let's say into a second or into a minute, and then stores the aggregated result for that time unit, which means metrics are very compressed. They're very cheap to store. You can store a whole bunch of them with long history going back. It's great. So we can have thousands of metrics. At last count, our system has over 100,000 unique metrics. When I say unique, I mean like the server name times the customer ID times the whatever. So there's 100,000 unique metrics. Java alone has is responsible for like half of them. Java has a bunch of metrics, right? And so that's very good. If they're time-based, you can go and you can zoom in up to the level of granularity, right? If you aggregate by the minute, you can't zoom in further than 1 minute. And that brings us to the weak point of metrics, which is you lose granularity. Because you don't store every data point, there are certain things you have no way of discovering through metrics. So I have an example. Let's say you're tracking service response times. You call a REST service, and you measure the response times, and you store the response time as a metric. And you go and look at a service, and you see that the response times on average are very high. But you go and you look at the service, and you say, okay, well, the average number of requests didn't change. Something weird is going on, right? It's an actual production use case we had from a different company I worked for, and we puzzled about that for a long time because all the metrics looked fine except for latency, and we couldn't figure out why the latency was high until we switched the metric granularity and started recording latencies at the millisecond level. And then when we looked at a specific second with millisecond data points, we saw that for most seconds it was fine, but every now and then you'd see an empty second with no requests and a whole bunch of requests at the end of the second, which is very weird. And then we looked at the garbage collection and saw that, yeah, there were seconds where garbage collection was taking place. And so all the requests would block and get pushed to the end of the second. And so instead of returning in a couple of milliseconds, they would all wait and return all at once at the end of the second, which is a very weird degenerate use case. And you couldn't possibly discover that if you aggregate metrics by the second or by the minute. You could still discover it if we had thought of going to look at the garbage collection metrics, which we didn't. And so we wasted a bunch of time, right? Usually you have a bunch of different symptoms, and you can get to the answer from different directions, but that's like the main weak point. The other main weak point, and something that happens in our system, for example, a lot, and I'm sure for you as well, engineers like clean graphs, right? If you have, let's say, 100 copies of a service running, 100 instances, you don't want to see 100 lines on the graph. It looks cluttered. So what do? You average them, right? You have, okay, well, let's say you have a load of 100 services. Let's have the average load. It's probably okay. It represents reality, right? Not really, it doesn't, right? Be very careful when you average stuff out or apply any kind of aggregation metric to a bunch of systems because it tends to hide granularity. Real example from a month ago, our Elasticsearch cluster in production was being weird. Queries were returning very slowly. We went to look at the load. It looks fine, 30%, less than 30% CPU load. It took us several hours until someone thought, okay, well, let's deaggregate. Let's remove the average on the load and look at the actual load for every service. And we discovered that 1 out of 400 nodes was at 100% CPU because some Puppet process was doing stuff with CPU. And so that one node was slowing everybody down. But it was 1 out of 400. The latency, average latency didn't move, right? And so if you look at metrics and you want to aggregate them to look clean, don't use something like an average if it's going to hide so much data, or at least be aware that, yes, you have to sometimes deaggregate your metrics to figure out what's going on internally, right? And so good ways of actually doing that would be looking at maximum, or looking at the top X, the 95th, 99th percentile. Those usually show you the outliers, and that's really what you want for most metrics. You don't really care about the average. Also, last pitfall, don't do average of averages. If you have a metric which reports the average of something, then you average over that, it becomes completely meaningless, right? So here's an example, right? I don't expect you to see it. Don't try to read the graphs. It's as incomprehensible to me as it should be to you. I took a random snapshot of our production dashboard, a random one of 50 production dashboards. This actually shows a production problem. Can you tell if it is? I can't. Honestly, I'm looking at it. I have no idea. The squiggles look okay to me. And that's the problem with metrics. They're not service level indicators. They're not supposed to be. They're investigation tools, and you look at stuff and you try to figure out what this system represents, right? As it happens in this case, this represents a problem which happens 4 services away from the dashboard at a different bunch of services which are on a different dashboard. But the symptoms are here. If we look at the top left graph, which is very spiky, it shows the amount, okay, I'll tell the story. It shows the amount of events that are rule engine processes, which does business heuristics, right? And it should be flat because the amount of events coming into the system is constant. The reason that it's spiky is very weird and has nothing to do with the rule engine, because if we look at the next graph over, which is the CPU load, CPU looks fine. It's not that the rule engine is busy. The reason it's spiky is because something upstream from it is sending spikes of events instead of a steady flow of events. And we went to investigate that, and eventually we got to our Elasticsearch cluster, which had weird load spikes, which we didn't have an alert for and we didn't know about. It has probably been going on for at least a day. And we started tracing that, and eventually we found that there was a Python script running on a desktop somewhere that was running a very heavy query exactly every so-and-so minutes, which is why the spikes are so steady. And so that would choke our actual production Elasticsearch cluster. And so everything else that was touching it would slow down for a while, develop a lag, and then catch up. Anyway, to summarize, this is why our security researchers no longer have access to the production Elasticsearch. Because they like Python. And, right, anyway. So metrics are not a good tool. So what is a good tool? What we talked about earlier, right? If we had, at this point, we didn't have a good SLI for end-to-end latency. If we had a good service level indicator that says the whole total system latency from end-to-end is higher than usual, we would have caught this in less than a few minutes, right? We would have caught it immediately. We didn't, and so we spent a whole day trying to figure out what went wrong and why is the latency up and stuff like that, right? And we might have not noticed it because we noticed it for an unrelated reason. So metrics are a good indicator tool. They let you investigate stuff. Logs are actually, I'm sure everyone understands logs. It's one of the oldest technologies. You know, when the first primal developer came up to a keyboard with a pair of rocks and banged out "Hello World," and then compiled it and it didn't work, the next two lines in history were printf before hello and printf after hello to figure out where the hello world broke, and that's how logging was invented. And so we all understand logs. Usually we dump stuff into logs to tell us what the internal state of the system is at that point. The benefit of logs is they're very granular, right? That's the opposite of metrics. Logs can be extremely granular because you can log a specific action. You can attach a bunch of context to it, what happened, you know, the IDs of the users or whatever it was trying to do, stack traces, anything you want. The downside of that, of course, is it's very expensive because you have to store all this data, you have to index it in order to actually be useful and search it, right? And in a distributed system, logs very quickly become just a massive pile of data which you can't reconcile. As an example, let's say we have 60 or to 80-ish microservices that a typical transaction will touch. Something comes in, an event comes into the system, it takes some route through a bunch of services, through a bunch of Kafka topics, touches a bunch of databases. Each one of those diligently writes stuff to a log. Can I take all this log data and then figure out if a particular transaction was okay and it reached the destination or not? Maybe if I take all this data and I spend enough time looking through all of the logs, I can reconstruct in my head what should have happened and if it actually did happen. But logs don't tell you stuff across services, right? They don't actually give you the transaction of what happened or the context of what happens to a particular flow through the system. They do give you a very detailed view of what goes on in a particular service. Unfortunately, oftentimes it's too granular or too good of a level, right? Because I don't know if it's for everybody, but in our case, we tend to overlog things very much. We log a lot of data, too much for my taste. It comes from the early stages of our system where we didn't have good observability, and the only tool we really had to figure out what was going wrong is logging. And so developers who can think of usually engineers have very good imaginations. We can think of many what ifs and many weird scenarios, and then we try to add log messages to cover those scenarios. So we had a lot of log messages from everywhere in the system. Now, when you're processing billions of transactions per day, and each one touches, let's say, 50 services, and each one logs, let's say, 20 messages, it quickly gets into the trillions of logs per day, right? And so at one point, we were running an ELK cluster for logs, which was bigger than our actual Elasticsearch cluster for production data, because we were just logging so much. And so this is like the danger of just relying on logs for everything. You do have to offload some of this work either to metrics or the stuff we're going to talk about a bit later, which is distributed transaction, which kind of fall in the middle between this the granularity of logs and the cheapness or inexpensibility of metrics. But for logs, I don't want to spend too much time on it because I hope everyone's pretty well familiar and it's a well understood technology. That's the main problem, right? You don't have the context and it's just very expensive to maintain. Because it's so expensive to maintain, usually you have to compromise on data retention, right? So right now, we can, for example, store 2 days of debug messages back and a month of errors back, right? And if you wanted to store more than that, we either have to log less or pay a lot more money to store a lot more logs, right? And even with compression and technologies, it's still the most expensive way to do it. So as I said, the reconciling logs across distributed transactions, that's something we faced very early on. One of the most common problems in a distributed system is you initiate a transaction at one of the end of the system, and it doesn't come out the other end. And then you're left wondering which service failed in the middle, right? Let's say you have whatever, an IoT system that a signal comes in, some service takes it, puts it in a kind of any message queue, let's say Kafka or Kinesis. Some other service takes it, tries to enrich it with data from a database, puts it in a second queue, and a third, and fourth, and so on, and then one of the services fails. Can you cache that, right? If that service fails in 1% of cases, and you don't know about it, there's no way for you to know that X transactions come in, but X minus 10% come out the other side, or 1%. The smaller the percent, the harder it is to catch. And so one of the ways to deal with that is to actually track the transaction from end to end. This kind of brings us towards distributed tracking and tracing territory. We still don't have, for example, in our case, a separate technology to do that. We overloaded this functionality on top of logs. What we do is, for every message which comes into the system, we generate a transaction ID and put it on the message itself, right? Because we didn't actually invest in any fancy technologies to do that, we attach the transaction to the actual data object, and so every service which touches the object then detaches the transaction ID and uses that in the log, so then we can go and we can actually connect all the different log messages to a specific transaction, right? Once you do that, you're halfway towards distributed tracing, right? Now you actually have the ability to take a single flow through your system, figure out all the things it touched. You still can't connect it to metrics, but at least you can find anything that touched it along the way, any service that touched it. And so we built around a lot of tooling around it, again, because we didn't have time to spend using an actual tool, which, by the way, is usually a bad idea, and there are good and bad reasons why you would do it, mostly for time pressure, why you wouldn't invest in a proper technology and build it yourself. It's always going to be a worse version if you build it yourself, unless you're like Google or LinkedIn or someone, in which case, good job. And so what we did is we took all of this stuff, which was actually in our logs and in the data object in the database itself, and then we built tooling around pulling out all the stuff related to our transaction and trying to figure out what happens to it. And we actually built a lot of functionality around it, which is now very hard to migrate to a proper tool. So that's the pitfall of actually building your own tracing system, a poor man's version, if you will, instead of actually using like a big boy tool. But still, that's something we did, and then it was pretty successful. All I have to do is, like as I said, put the context in the log, and then reconstruct the transaction flow. We actually had a bunch of visualization written around it. You could take an automation run, which is our automation framework, which runs every 5 minutes, as I said. Take a specific run, find everything it touched, figure out if it's working. One of our customer success people or a salesperson can go and look at what happens with a particular customer. If they're going to go to a sales demo, they can quickly pull up the state of a customer to see if it's missing transactions or anything wrong. So it actually provides actual business level value to people because they can now go and see if a specific thing is working or not. Right? It's especially important if you're about to demo this feature and you want to know that the feature is working, which, by the way, it always is. Just saying, for future customers. And so this is like our bastardized version of it. And so let's talk about what the actual real world production use case would be, where you want to use a real tool, not invent one yourself. That brings us to actual distributed tracing, which is a set of technologies to track transactions across the system. So let's define a couple of terms here, right? A transaction is not a specific term. It's not like a database transaction. It's more of a single flow of execution across the entire system. If you're in a microservices environment, for example, and you have REST services, a transaction would be starting from, let's say, the client or the browser, calling a service, any service it touched, any databases it touched, all the way back to the client, and synchronously, right? Or if you're in an asynchronous system, some event comes in, it gets piped to a bunch of other services. It might split. An event might become 2 or 3 messages. It might get stored and then batched later. So it's kind of hard to define exactly what a transaction is, but pretty much anything logically related to that initial event, that'll be part of our transaction, right? And so you want to chunk this transaction up, and so we define what's called a span. A span, this term, by the way, comes from Google. Google are pioneers in the area of distributed tracing. A long time ago, they built a system called Dapper, and published a white paper about Dapper, which is their distributed transaction system, tracing system, which is fascinating. By the way, I encourage everybody to read Google's Dapper paper if you're bored. But if you're not and you want to do something useful to your work, there are 2 books Google published called the SRE book and the SRE handbook, which are not just for site reliability engineers. I think every engineer should read the Google SRE book. It's fascinating. It has a lot of information about the way Google engineers think about reliability and observability of systems. I think anyone who writes any kind of code which ends up in production should read this book and figure out what it is that one of the largest companies in the world actually looks and thinks about it. And so they define what's called a span, and a bunch of technologies which were modeled on Dapper adopted this terminology. And we'll talk about those in just a bit. And so a span is a logical unit of work which makes sense to measure. So for example, a database call would be a good span, right? It goes from one process, your application, to another process, the database, and then back. And that's a useful thing to measure. Or a call between 2 services. You have service A calling service B, right? So we initiate the span in service A. It spans the RPC, the HTTP call, or the Kafka message, and then it ends at the entrance to service B. And so we can measure this span and have useful information about it. Things like latency, when it started, when it ended, any kind of context we have on it, right? And in the distributed tracing, we have 2 levels of communication. We have the inbound message, which is usually a small context object, which has the transaction ID, maybe a little bit of information about the origin of the span, the previous service, start and end date, things like that, but a very small amount of data because it travels with the message along the system. It's inbound, right? And you don't want to overload too much data on the inline data propagation. And then every service that gets the message looks at the context and then emits a much larger object out of band, right? So similar to logs, right? In that way, distributed tracing is very similar to logs, where you have instrumentation in your application in certain places to emit outside this process a large log object, which somebody else collects and does something with. We'll talk about exactly who collects it and what they do with it. Basically, once you get all of these transaction objects and you put them together, you can have a good idea of what happened with the transaction throughout the system, right? You can reconstruct it. In the same way you could with logs, except here it's much more tightly coupled to the actual execution flow. And you can figure out how long each span took, and you can actually get some useful data out of all the spans. And so pretty much it looks like this, right? And it doesn't matter if it's HTTP or Kafka or whatever. Usually you want to put the metadata that travels, the transaction ID and the context, on the metadata of the channels. For example, with HTTP, you would put this in the headers, because that's what headers are for. gRPC also has metadata. Something like Kafka, just out of curiosity, who uses Kafka for something? There's like 3 people. That's very poor. So anyway, so Kafka or RabbitMQ, any kind of queuing technology usually has metadata you can attach to the message. So you don't want to put it in the message itself. And then you take the transaction context, put it on the object, and it moves from service to service. Every service sees it, it detaches the metadata from the message, emits a whole transaction span. And so that's a pretty hard problem to solve, because instrumenting a whole bunch of places in your application is a lot of effort, right? We'll talk about ways to make it easier in just a bit. But generally, think about it, distributed tracing the same way you do about logs or metrics, right? It's the job of the developer to instrument the application in the places where it makes sense to emit this information, right? So with logs, you usually have some kind of framework or infrastructure for logging, and then wherever it makes sense in the code, you call log this. Like you have an exception, you put it to a log. You have whatever, some interesting thing that happens, you put it in a log. Same thing with metrics. The application does something interesting, which is worth measuring or counting. You call the metric system, and it emits that metric into the collector. Usually, you don't do it manually. A lot of time, you build some kind of infrastructure which abstracts away all this stuff, right? So you don't measure every HTTP call, right? You have some kind of wrapper for the HTTP client, which automatically logs every HTTP call, and it sends a metric. You don't have a database driver, and then you manually do stuff. You wrap the database driver and instrument inside of it, and then you get much better coverage, because every service which uses your database wrapper will now automatically trace and log and send metrics and all that stuff, right? So you save yourself all the trouble of actually going and instrumenting code line by line manually, right? And same thing with tracing, right? One of the problems is there are so many frameworks, we'll talk about them in a bit. There are so many ways to do distributed tracing. You want a common way of actually instrumenting code, and there are tools which let us do that. I'll talk about them in a bit. So back to the trace, let's look at the actual transaction trace in a distributed tracing environment. If we look at the timeline of a graph, right, of a transaction, which goes, in this case, right to left. Your case would be left to right. So let's imagine we have two services, service A and service B. We send a web request to service A, which is synchronous, and it does a bunch of work, goes to the database, and then service A sends a Kafka message or an asynchronous message to service B, right? So if we map that as a transaction with spans, would have the first span, which is service A getting the request. It's synchronous, and so all the other spans which belong to it are within that first span, right? They happen inside of it. They're children of that span. This is a relation we define for the purpose of distributed tracing. And so maybe inside it calls a function. Let's call it span B. That span goes and calls a database. That would be C. Gets the result, goes and calls another service. That's D, and then does other stuff. When all of this is finished, then the first service's span A is closed. That's what we measure, right? So the whole transaction here is both services. And then service A sends a message to service Z. This message is not part of the first span, right? You can see that it's not part of A. Span F, in this case, the gray one, it follows from span A, right? And so it's not a child of A. They're not dependent on each other. They're siblings. One follows the other. Now, if we go and we represent this on a graph, we'll see some kind of waterfall graph similar to how you would look at, let's say, in a browser, a network latency graph, something like that. So once we have this, we can now take this and answer very interesting questions. So some of the questions we can answer with distributed tracing are business related. Pretty much all the questions are business related ultimately, right? Because we're running a business and we want to, the customers to pay us money. But some are directly related. For example, there are questions which are very hard to answer with logs and metrics and automation and all the other tools we have for observability, such as, are we currently within our SLA to the customer? If we define the SLA, in our case, for example, as being end-to-end latency, because our product, what it does is it looks at cloud events and tries to decide if someone has hacked the customer's account. And the quicker we can decide that and block it, the better value we provide to the customer. One of our primary service level indicators is processing latency, right? From the moment we get the event, the login event, let's say, until the moment we kill the customer, the login session, that's how long the attacker has in the system to do damage, right? And so the less that is, the better service we provide. And that's one of our primary SLIs. But for something like a website or a web application, your SLI would be load time or average load time, or for a mobile app, talking to the backend, whatever. Your SLI is defined what it is. But knowing if you are within the SLI, it's very hard if you don't have end-to-end transaction visibility. Because all you have to look at are individual service logs or metrics which are specific to a particular service or a particular action, and you can't connect them end-to-end. Or you can, right? You can do it in other ways. You don't have to use distributed tracing, but it's expensive and hard. Once you have distributed tracing, you can start answering those questions much easier. This is what I meant earlier, where you don't have to use a specific technology. There are trade-offs to all of them, right? And so the trade-off for not using distributed tracing for these kind of questions is you'll probably pay more, or you'll do more work manually and stuff like that. But you can still do it. So answering stuff like, am I within the SLA? Is my end-to-end latency X, or within certain boundaries? Or is my load time, or CPU, whatever it is you define, becomes much easier. The second thing that happens is it becomes much easier to answer the second question in observability, which is what exactly is broken? Now that we have a full trace of what happens in the system, we can zoom in to a particular part and see which span is responsible. Like, for example, in our case, because we care about end-to-end latency so much, we can now look at every span and how long it took, and we can find the spans that took the longest and figure out why that is. Or if a particular span suddenly goes from latency X to latency 10 times X, we can try and figure out why that is. And then obviously we can extract much more sophisticated application performance metrics out of distributed traces than we can from just normal application metrics or system metrics, right? We can now actually measure things and convert them into a metric that are much higher level than just a particular service. Again, end-to-end stuff and the like. Once we have this, we can complete the whole picture of what's actually going on in the system, right? And so the way you collect metrics, as I said, is you have to instrument the code. I'll actually hopefully have enough time to show you an example of that. It's usually either very hard because you have to do it manually, or very easy because you use a framework, and there's no in between. Then you collect all the traces. The problem with collecting traces is it's actually even more data than you would with logs, right? It makes sense to collect a bunch of spans. You usually have between one and, let's say, a handful of spans for every process. And so you take the number of transactions every day, you multiply it by a number of servers, multiply it by a number of spans each one emits, you quickly get into trillions of objects that you have to store. So you can't really do that. So usually the answer that most people who use distributed tracing is to do sampling, right? You don't need every transaction. You just need a representative sample of the important transactions to get the idea. So here you have a trade-off or some kind of scale between the granularity of logs, the lack of granularity, but the low cost of metrics. And you can define where you fall on that. Classic example is in Google's case with their Dapper system, they sample one out of every 10,000 transactions, right? They don't collect every metric. It's completely impractical at the Google scale. So they sample one out of every 10,000, and that still gives them enough information to actually know what the state of the system is, right? And there are different ways to do it. You can sample adaptively. Let's say I want every service to emit 100 messages per second, traces per second. Or you can sample by percentage or something. Just the pitfall here is if you decide to sample one of every X messages, which is something we tried doing, the problem is if you have different types of messages. Let's say we have an event which happens 1,000,000 times a day, and a different event which happens 1,000 times a day. If you just randomly sample one out of every 1,000 messages, we're almost certainly going to miss the second event and have no information about this, and have a good sample size about the very frequent event. And so you need to apply some intelligence to how you actually adapt sampling here, and then you can obviously change it. So for example, for automation runs, in our mechanism, they're not subject to sampling. If an automation run starts a transaction, it always gets collected. All the traces get collected, and only if users or normal system operations transactions, they get sampled one out of X. Because we want to have the full context of every automation transaction. Right. Once you have all this data, what do you do with it? Obviously, right, you want to get some interesting insight out of it. So you dump it on some kind of index, or you do some kind of backend work for it to actually make it searchable and queryable. Then you query it and you visualize it. Now I have some examples of how you can visualize it to get useful data, but the sky is the limit. And so I talked about some open standards for this, or some standards for tracing. There are several projects called OpenTracing, OpenCensus, and OpenMetrics. And like every standard, like each one of them claims to be the standard for distributed tracing or distributed transactions. They're not, but they're actually very good projects. OpenTracing in particular has support from CNFC, so the Cloud Native Software Foundation. And it's adapted quite relatively widely. Almost all the tools, the common tools that we have for tracing today support OpenTracing or have some kind of connector to OpenTracing. OpenMetrics tries to do for tracing, same thing for tracing and metrics, right? So it has a common interface that is vendor neutral, which lets you instrument all of your code in a way where you can switch the backend. Let's say today you're using whatever Elasticsearch, and tomorrow you want to use Zipkin or whatever, some other system. You don't have to go and rebuild all of your instrumentation and code. You instrument once, which emits traces compatible with OpenTracing. It emits metrics compatible with OpenMetrics. And then you can plug the backend and change it as much as you want. You don't have to go and do all the expensive work of actually instrumenting every piece of code separately, right? And all of them usually come with libraries which instrument common things. For example, for .NET, OpenTracing instruments HTTP calls automatically, right? So any requests and responses get traced automatically, and that means it can detach the transaction context, open the span, close the span, all of this stuff happens for you. There's very little code you actually have to write. Same thing for common things like Spring and Java. And so OpenTracing specifically tries to solve the very narrow problem of how do you propagate the trace context from service to service. which is a pretty hard problem, right? As I said, there's different ways of actually calling services. There's HTTP, RPC, Kafka, RabbitMQ, all this stuff. And each one has different weird edges and edge cases, and you have to cover a bunch of languages. And so they solve this one specific problem, and they leave everything else, like how do you collect the traces, what do you do with them, for other tools to solve, right? And so we said, usually you sample, you index, and pretty much every system that's open source that supports distributed tracing uses either Elasticsearch or Cassandra or both as the backend. They're very common. We'll look at some examples in a bit and see how you can actually do that relatively cheaply, how you can integrate it very cheaply into your system. Now we get to the interesting part of it, which is how do you visualize traces, right? So we have all this wonderful data. We have logs, we have metrics, we have traces. We've looked at logs. You don't usually visualize logs. You usually search them. Metrics are very obvious how you visualize. Usually they're histograms based on time, and so it's obvious. So how do you just visualize traces, right? Which is a trace is it has a time component. It also has a transaction component, and there's a bunch of ways you can visualize it. The two most common ways are either building metrics based on histograms, so time flows, the latency of a span or latency of a transaction over time, or building waterfalls and flame graphs, which are more like CPU sampling, where you take a trace and you map all the different spans on a graph and show how much each one took and the relationships between the different spans. And so you have a waterfall latency graph, as I said, very similar to what you would do with network latency, for example, in a browser. I've seen very weird systems as well, people that customize their own backends for transactions, where they display the transaction in interesting ways. We actually have a homegrown one as well, which looks nothing like any of the common systems. Right, and so that brings us to a quick set of tools. So there's a billion tools for it, right? Generally, they fall into one of two categories. There's self-hosted and there's managed services, which you can buy as a SaaS, right? You don't really have to remember all of these, but just, I'll give you a quick list of screenshots so you can get a feel of what the tools are. I specifically avoid, selling products. I don't care about, which one you use. Pick whatever works for you. I tried not to make the whole talk very product-centric, but I just want you guys to get a feel of what the UI would look like. What is the actual benefit you get from using the tool, right? And so on the left, we have all the self-hosted tools, Zipkin and Jaeger. Jaeger is also an open source tool that's been adapted by the Cloud Native Foundation. It's being incubated, so it's a very nice open source tool. There's a few of them, a couple of paid ones. One very interesting one is Elasticsearch, right? As I'm sure a lot of you use Elk for logging. And so Elasticsearch, as of version 7, if I'm not mistaken, have an APM module, which is like a small service which can collect application metrics and traces and store them in Elasticsearch. And so it overloads this distributed tracing functionality on top of your normal Elk. So if you have Elk installed, it's very easy to also put distributed tracing into it. It's compatible with OpenTracing, so if you instrument stuff, you can switch it out later. And it breaks this friction of, well, this is a huge task, right? How are we going to do this tracing stuff? There's, we have to spin up a database, blah, blah, blah. If you already have Elk, it's a very small gap to jump to OpenTracing this way. And I highly recommend it. Most of it is free. Some parts of it, which are related to analytics, which are not in the free version, and unfortunately, they're locked behind actually buying a subscription. But most of the stuff is actually free, and it's very nice to play around with. So let's look. It looks like this, right? So this is a screenshot of Elastic APM. This is a transaction analysis view, right? As you can see, you have a flame graph, right? This is a random HTTP transaction, which is built out of a bunch of spans. And so if you look at this, there's a bunch of ways to visualize this. In this case, it's looking at one transaction. You can also look at aggregations from many different transactions that looks the same and see average latencies and stuff like that. But this is very common. Pretty much every tool which does distributed tracing will have a graph that looks kind of like this, or a kind of visualization that looks like this, right? Which is a latency graph. There's another tool I like a lot, which is Jaeger. It's open source, cloud native, as I said. In addition to the latency graph, they have a very cool feature of comparing two different transactions. So what this does is it gives you the difference between two different sets of transactions and the changes in different services, which I like a lot. I think it's a very cool way of representing changes in your infrastructure. If you look at a bunch of traces from yesterday and a bunch of traces from today, you want to see what changed. If you can also somehow tie this to your deployment system, if you have CI/CD or a build server, and you can say, okay, well, yesterday a service got deployed, and now we can see that the latency of the service went up by X% between two different traces, that's really valuable information. That actually answers pretty much all the useful questions you can have about observability of what changed, why, and what caused it, right? And you can trace it back to a specific commit or a specific build, which is a very cool ability, which I would love to have in our system. We're not there yet, but we'll eventually get there, hopefully. Zipkin is very similar to that. It has, again, a waterfall graph of latencies. This is an example I took from Zipkin running over Kafka, which is much harder to do because instrumenting Kafka is much harder. It's not as easy as, for example, HTTP with headers. But Zipkin comes with out-of-the-box support for Kafka and a bunch of other messaging technologies. Very dark slide from Apache Skywalking, but it basically it has all the other stuff we showed about, and also this cool way of actually visualizing your system dependencies, which is not useful as far as I can tell. I don't think I'd ever use this, but it's very cool for demos. Or if you have a new employee coming in, you can show them, well, this is our entire system. This is the data flow in the system. That's pretty cool. That's probably the only actual use I can think of it. Finally, you have AWS Xray, which is Amazon system. Every cloud provider has something. So Azure has App Dynamics, so App Insights, sorry. And every cloud system has something similar to that. AWS has Xray, which in very typical Amazon fashion is completely incompatible with OpenTracing. I'm showing this because I like the graphs and the way it actually visualize service latencies between different services, but there is no way to instrument your application with OpenTracing and send this data to Xray. If you go Xray, you're locked to Amazon, and it's very annoying, and that's something that happens a lot with if you use AWS, unfortunately. And so before I finish, I just want to show you a quick example of how you actually do this in code. As it happens, I do have some code here. So this is a very simple set of services, small .NET Core backend service and .NET Core frontend service. This is the only code I had to write to make it emit traces to Zipkin. And I could replace 2 lines of code from Zipkin to Jaeger or whatever, and it would actually work with the different system just as well. So all I had to do was actually initialize the tracer here and tell it where to send it. I have Zipkin running on the same machine in a certain port. Normally, it wouldn't be on the same machine, probably somewhere else on the network. And so the Zipkin library automatically hooks into HTTP client and HTTP server. It will automatically attach the transaction context to every web request and detach it and create spans for every web response. And does a bunch of work for you. And so this is why I picked this example, because this is the minimum amount of code I found of all the various technologies that you had to write to actually have distributed tracing in your system, right? And so as you can see, this is 2 services, right? There's no code related to tracing in either service, right? Everything is just in the initialization, and it doesn't actually do anything fancy. All the front-end service does is call the backend service. Right? There's nothing specific here to traces. It's just when we create a client, we create one that supports the tracer. And in the backend system, there's also, as I said, no special code related to tracing, nothing like that. So the whole instrumentation was actually very seamless. If you run this thing, let's see if it actually will run, because you never know with live demos. And hopefully, if everything works okay, as you can tell, it refuses to run, but we'll give it another try. And this is weird having .NET Core in a Visual Studio running on a Mac, but it actually works most of the time, or at least like half the time. Okay, it works on the second try. And so if we go here, it's a very simple web application. All it does is return the current time. We'll click it a couple of times. Then we'll switch over to our Zipkin servers. I have Zipkin running in the background, and then we can go and we can find some traces. So Zipkin has a very slim interface. All it does is just show me the actual traces. We can go into a trace, right? And you can see that this trace has 2 spans. It has a front-end server and a back-end server span. If I had more functionality in the service, I'd have probably more spans, like a database call or whatever, some kind of RPC. And we can go into each one of them and get some details. And in this case, all the stuff I actually overload on top of the emitted trace, I could have exceptions here. I can have any kind of tags to go and search for the traces later. I would see them here. And they have a cool feature called system dependency graph, which is kind of similar to what we showed earlier. We can go and can look at their cool UI and show the system dependencies. And our entire system looks like this. There's exactly 2 services. And we can look at one of the services and see who calls it. So the backend server was called 7 times by the front-end server. Wonderful. We have metrics, we have graphs, all the cool stuff we ever wanted from our observability. So just to summarize real quick before we finish, it's not about technologies, right? It's not about specific products we're going to use. We want to actually to sleep at night mostly, right? I don't want to be woken up by alerts. And so we want to instrument as much observability as we can into every system. When you approach an existing system, it's usually extra hard because there's a lot of work you have to do to go back and instrument existing code. And so for this, and this is something I found over the past year and a half, usually engineers, when they try a new thing, a new technology, they have the tendency to go to some non-critical part of the system and try it there, just in case it breaks something. With stuff like tracing and observability, counterintuitively, usually you should go to the most critical system and instrument that and get observability over that because you get much more value immediately. Right? If you're going to add traces or open distributed traces to your system, go to the 2 or 3 services which are the hardest or the most important in your system, instrument those, and then see if you have actual value from that, and then you can justify going to all the other services and instrumenting them. Right? If you go to the least important service and you instrument and you have traces out of that, it's not going to be useful. There's a reason it's not important, right? And so that's my advice. Thank you very much for coming to the talk. Hope you enjoyed it. Here to answer questions afterwards.